In real life, almost no edge is perfectly sharp. But in game art, we often use razor-sharp edges that can lead to harsh shading and an unnatural look. Controlling vertex normals is the secret to fixing this. It's one of the most powerful ways to improve visual quality without increasing your performance cost. Before we dive into the practical techniques of how to control them, let's take a moment to understand the basic theory behind normals and how they actually drive shading in real-time rendering. Let's start by looking at the normals of a sharp-edged cube. You'll notice 3 small handles appear on every vertex. Why 3? Because each of the 3 faces connected to that vertex has its own shading direction. What we are often not thinking about is that sharp edges split vertices at render time, since the GPU needs separate normals for each face. So even though we're not adding visible geometry, the real vertex count still increases. Most software, like Blender, only displays the number of vertices that we can interact with. So this increase is invisible unless you use an add-on or script that calculates the final vertex count. However, Unreal Engine shows the true rendering vertex count. In Blender, our cube with sharp edges shows 8 vertices. If we import that same cube into Unreal and open the static mesh editor, you'll see that the vertex count is now 24. Now, let's smooth the cube and send it back to Unreal. The vertex count is reduced to 14. But why 14? If we look again to the normals of the cube, there's only one normal handle per vertex, and the direction of that handle is an average of the surrounding faces, as they are actually connected. So, we should have 8 vertices, right? Not exactly. Even though this video is mainly about normals, it's important to mention that there are other factors that also split vertices. Just like sharp edges, UV cuts create additional split in the vertices. A single vertex can only hold one UV coordinate. If a UV seam cuts through an edge, the engine must split that vertex to hold 2 different UV coordinates for the texture. So, if we edit the UVs of our cube and remove all seams, then re-import the mesh, we return to 8 vertices. This demonstrates that in games, optimizing based only on triangle count isn't enough. Going back to our smooth shaded cube and its normal handles, our goal now is to control those handles to achieve more natural shading. After all, the basic, perfect, sharp edges from 3D software are almost non-existent in the real world. One common method is using support edges. If you've done subdivision modeling before, the principle is very similar. Let's compare a cube with normal smoothing applied and a subdivided cube. The subdivided cube becomes a sphere, while the smoothed cube stays a cube. But visually, it's trying to become a sphere. Now, if we select the subdivided cube in edit mode and insert a loop cut, you'll notice that moving the loop closer to an existing edge makes the shape sharper. Placing these support edges around the rest of the cube brings it closer to its original shape, while keeping soft, controlled transitions on the corner. Let's apply the same idea to our simple, smooth shaded cube. Adding a loop close to the edges immediately makes the shading sharper in that area. If we continue adding support edges, the shading begins to look much more intentional and visually correct. If we take a closer look at the normal handles now, we can see that the handles on the flat surfaces point straight outward, while the corners average their direction smoothly. That's what we want. Flat normals, where surfaces should look flat, and average normals, where transitions should be smooth. One thing to keep in mind, if you modify the mesh in these areas later, you'll need to be careful. These support edges aren't meant to change the overall shape. They only exist to control the shading. If you move or deform them, the normals will tilt. which can introduce some undesirable shading artifacts. That said, there are some advantages to this method. For one, it's easy to remove the support edges without altering the base mesh. It also helps with UV stability. Since your seams can be placed right at the edge, the UVs are much less likely to slide. Plus, if you ever need to subdivide the mesh, these edges will maintain the intended silhouette. The main trade-off is the density. It requires a higher polygon and vertex count, and because the edges stay quite sharp, it might not provide the most natural silhouette in every situation. Let's look at another popular approach to handling those sharp edges, the bevels and weighted normals technique. Many artists simply add bevels to their models to create rounded corners, often using the default settings, and call it a day. If you look quickly at the cube with the newly created bevels, it might appear correct. But in reality, the shading is still too soft. Let's take a look at the normal handles. The handles on the main flat surfaces are not perpendicular to the surface as they should be to achieve an accurate, flat look, unlike what we achieved with support edges. To fix this, we need to adjust the normals. There are several ways to do this, which we'll explore in future videos. But for now, we'll keep it simple. In Blender, select the faces that need normal correction. For this cube, that's every face except for the edges and corners. Once selected, press Alt-M to open the Normals menu and select Set from Face. This action forces the normals on the flat surfaces to align perpendicularly to the face, ensuring the soft shading becomes perfectly flat. The difference is much more apparent now when you compare the original cube to the fixed one. To wrap things up, let's do a side-by-side comparison of the three techniques: sharp edges, support loops, and the bevel method. To keep the comparison clean, I've removed all materials and UV seams so we can focus strictly on the geometry and shading. First, the sharp-edged cube. The shading and silhouette look unnatural and harsh. This version uses 24 vertices and 12 triangles. Next, we have the smooth cube with support edges. While the shading is much better, the silhouette remains sharp. However, the density has jumped significantly, up to 56 vertices and 108 triangles. Finally, the beveled cube. Here, we get the best of both worlds: clean shading and a rounded silhouette. Interestingly, it only uses 24 vertices and 44 triangles. In game development, the real cost on the GPU is usually vertex processing, rather than just the triangle count. A single vertex carries a lot of data, from position and normals to UVs, tangents, and weights. Because of this, you should prioritize optimizing your vertex count first. When comparing the sharp cube to the beveled one, they share the same vertex count, meaning their performance cost is nearly identical. While sharp edges will always have their place, bevels should be your priority whenever your model can benefit from that extra visual polish. One last tip: keep in mind that game engines usually count more vertices than your 3D software shows. Every hard edge and UV seam acts like a cut that forces the engine to double count those vertices. This means that clean UV layouts and smart shading are just about looks. In many cases, they are just as important, if not more so, for performance as having a low triangle count.